Hey everybody, Dr. A here, and in this video we're going to be providing some background information and go over the governing equations related to columns, okay? So this is for the purposes of an introduction to columns for a mechanics of materials or structural analysis course. So let's go ahead and get started. What are columns? Well, columns are vertical compression members that primarily support axial compressive loads, okay? Now, in general, columns may fail by either compressive yielding or buckling, all right? So let's go ahead and sketch some things out. When we say columns are vertical compression members, what we mean is we have a member here that is somehow restrained at its ends, and it's supporting an axial load that is causing it to compress, okay? So let's say that this column has a length of L, and it's supporting a load P along its axis, okay? So that's what we mean by vertical compression members, okay? Now, in general, we say columns can fail in either compressive yielding or buckling. So there's an or statement here, all right? Now, let's talk about each one of these very quickly. When we talk about compressive yielding, okay, what that means is the column material will yield due to that compressive force. Now, during compressive yielding, when we look at that failure mode, what generally happens is, I'm going to draw another version of a column here, but I'm going to draw it a bit wider. If we have this compressive load on this wide column, when we talk about compressive yielding, what will tend to happen is the column will shorten in length, okay, and then it will bulge out. Let me draw that a little bit better for us. It will bulge out, okay? Okay, now when it does that, it will then develop some shear cracks. Usually these are diagonal, and it's doing that because the material itself is yielding, okay? Now, where have we seen this before? We've seen this kind of behavior before when we talked about Poisson's ratio earlier in a mechanics of materials type of course. So this is the Poisson effect, where you have a shortening in one direction and a bulging in another direction. If you continue to increase this load P until failure occurs, that will happen. That will occur in what's called compressive yielding. So I'm going to make a note here. We're going to say compressive yielding occurs in short, stocky columns, okay? So that's compressive yielding. That's one failure mode. The other failure mode that we're going to talk about a lot in this video is buckling, okay? Now, what is buckling? Well, buckling occurs whenever you have a column that is long and slender, okay? So let's say that we have a column here that's much longer, and it's not very stocky, it's very slender, okay? So what will happen when we look at this kind of failure mode is the shape of this column will tend to bow outwards like this, okay? Draw that a little bit better. We'll tend to bow outwards like this, okay? This is called buckling, all right? So buckling occurs in long, slender columns, all right? Now, in this video, moving forward through this video, I'm going to exclusively talk about buckling, okay? So for the purposes of this video, we're gonna just go ahead and assume that all the columns we're talking about in this video are long, slender columns, okay? Now, in a later video or in other courses, maybe a structural analysis course or a steel design course or a machine design course that mechanical engineers may take, you might go into what is the separation between a short column and a slender column, okay? There's what kind of threshold will we use to define what it means to be a short column versus what it means to be a slender column. But for the purposes of this video, we're gonna only consider slender columns. So everything I'm talking about henceforth will be a slender column, okay? So let's talk about that. So for slender columns, the force that causes buckling is called the Euler buckling force. And this is named after Leonhard Euler, who is a famous pioneer in physics and engineering and mathematics, developed a lot of theories across all of the physics, mathematics, and engineering fields. So what Euler ended up discovering is that the force that causes a column to buckle, we're going to call P sub E, and that's going to be equal to pi squared EI over this term called K times L squared. Okay, so this is what we call the Euler buckling force. Okay, now pi is pi, that's 3.14159, etc. Okay, what are these other terms? Well, we should be familiar with them. E is Young's modulus, or modulus of elasticity, okay? I is a moment of inertia, okay? Now, later on in later videos and in later courses, you're going to do a little bit more about which moment of inertia will be utilized in this formula. But for now, we're going to label this as the moment of inertia about the weak axis for now, okay? And so what I will be equal to for the purposes of this introductory video is going to be the minimum of Ix or Iy of a member's cross-section. And like I said, again, when you get to more details in column analysis, you're going to kind of dive into which I value you use under different circumstances. That'll be partially related to how a column is restrained either at its ends or intermediately between its ends. But for now, for the purposes of this introductory background video, we're just going to say we're going to look at the smaller of either Ix or Iy to be the moment of inertia we're interested in, okay? Now, what are these other terms here? Well, L is simply the column length, okay? And then K is called the effective length factor, okay? So let me ask this question. What in the world is this thing called K, the effective length factor? And furthermore, what is K times L? Well, if you multiply KL together, like what shows up in this formula, KL collectively is called the effective length, okay? Now, what K represents is the basically the percentage or the portion of the length L that will buckle, okay? That's kind of what it represents. So for example, let's say that we have a column that is restrained by pin connections, okay? So let's say you have a column that's restrained by these pins, and it's supporting, compressive force P. Now, when P gets to be P Euler, what will happen to this column? Well, it's going to buckle, okay? It's going to bow out like this, okay? So the length of this column is L, all right? And when you have the restraints being pins at the ends here, K, the effective length factor, is going to be equal to 1.0. Okay, so what that means is 100% of the length of this column is going to buckle. That's one way you can think of it. All right, so KL will be the length of the column that is bowing out, that is buckling. Okay, so in that case, K is 1. Now let's talk about some other restraints that we could encounter. What if we have the extreme case of you have total fixity here? Okay, let's say you have a fixed scenario, and you have that column subjected to the Euler buckling force. So how is this column gonna bow out? Well, there's gonna be a taper near the ends that are fixed. Okay, so if I dash this in, there's gonna be a taper here. Then this thing's gonna bow out and it's gonna taper back. Okay, now the total length of this column is still L. Okay, so I'm gonna put this this total length L. That's the actual geometric length of the column. But how much of this is going to buckle? Well, here, this is the approximate amount that we are considering will buckle. So that's KL. So the theoretical K value for a fixed column, K, is going to be equal to 0.5. So theoretically, what we are considering here is that about 50% of the length of that column is bowing out or is buckling. Okay, so that's, again, one way we can think about that. All right, let's look at another case. Let's look at the case where maybe we have a pin connection on one end, and on the opposite end, we have a fixed connection. Okay, and again, we've got P Euler here. P Euler here. All right, and so when this bows out, we're not going to have a taper at the pin connection. It's just going to bow out directly from the pin connection, but you will have a taper on the near the end where the fixed connection is. So I'm going to draw that a little bit better for us. You have a taper here. Okay, so again, the total length of the undeformed column is still L, but what about the length that we're considering that is buckling, that is bowing out? That's KL. And so here, in this case, the theoretical K value is going to be equal to 0.7. All right. Now, when you look at the case that we just talked about, a pin on one end and a fixed connection on the other end, it does not matter if the fixed connection is at the top and the pin is on the bottom. All that matters is that the pin is on one side and the fixed connection is on the other side. Okay, so the same case, K would still be 7 if the fixed connection was at the top and the pin was at the bottom. It's just it would be bowing out symmetrically, with a taper on the fixed end. So if this was fixed up here, it'd taper, and then it would just come back here if the fix was at the top. Okay. Now, these are not the only K values. There's some other situations where K could be a little bit different, but for the purposes of this introductory video, these are the only three I'm going to present here, okay? So that is the general background information. Now, we have our governing equation here. We've defined all of these terms here, okay? There is another version of this equation, okay, that we might encounter. So let's talk about that really quickly. So we want to recall something. Recall that the radius of gyration, which we call r, is given as r equals the square root of I over a. So you might remember that from learning about section properties. So what we can do is we can repackage this version of the equation, of the Euler buckling force equation, into a version where we use the radius of gyration and cross-section area A. So A is going to be again, the cross-section area of column. So you can rewrite the Euler buckling equation as pi squared EA over KL over R quantity squared down in the bottom, okay? Now, whether you use this version of the equation or the version I presented up here does not matter. You will get the exact same answer in either case. It just depends on which cross-section properties you have readily available for you. You could use either version of those equations and get the same answer, okay? Because they're related by this radius of gyration definition here, okay? Now, this term KL over R collectively is called the slenderness ratio, okay? So the reason why this is packaged in kind of a strange way with KL over R in the denominator and squared is because whenever civil engineers get to the steel design course and whenever mechanical engineers get to the machine design course, you often make some decisions on columns and other compression members based on this slenderness ratio. So even though this is the purpose of this video is meant to be for, in an introduction to the topic in mechanics of materials or structural analysis, I do want you to be aware of this idea of a slenderness ratio, that you will do something more with it in a later class, okay? Now, one more step forward with this. If you want the stress, okay, this because PE is a force, right? PE is a buckling force. If you want stress, all you got to do is the following. We can say the Euler buckling stress is sigma sub E. All you got to do is take your value for PE and divide it by the cross-section area. Same area that we are dealing with here, okay? And you get what's called the Euler buckling stress. So sometimes you might come across an exam question or a quiz question where they ask for the Euler buckling stress. You just you calculate the Euler buckling force first, and you divide by a cross-section area, and boom, you got stress, okay? Now, let's make sure we understand the units here, okay? Well, I'm going to put in green here, unit check, all right? So this should be a force, right? So pi is unitless, okay? E has units of force over length squared, right? That's the units of E. What about A? Area is length squared, okay? And then we divide by, what about this slenderness ratio? Well, K is unitless. K is unitless. L has units of length. And radius of gyration has units of what? Also has units of length, okay? So if you track what should be canceling here, the units of length cancel in the denominator, and then the length squared and the length squared cancel up in that numerator. So you end up with units of force for P Euler. And I encourage you to take some time and do your own unit check for this version of the Euler buckling force to convince yourself that the units come out with units of force. They will, but maybe do that on your own to convince yourself of that, okay? One other comment I like to make, because this could show up on a quiz or an exam, which is it's a great stylistic question to make sure you understand what's happening. Here's a question for you. If we were to double the length of a column, how much will the Euler buckling force increase or decrease? Okay, so think about that. If you were to double L, how much will the Euler buckling force increase or decrease, or would it change anything? Okay, so you can answer that question by looking at this formula or the original formula. Again, let's look at this one too. If you were to double L, if L became 2 times longer than it was originally, will E increase or will P sub E increase or decrease, and by how much? So maybe pause the video if you want to answer that question yourself, because I'm about to tell you the answer, okay? Here we go. If we were to, for example, double L from one number and then double it to a new number, P sub E will increase by a factor of 4. It will not double, it will quadruple. Why is that? Well, if you double L, if you say instead you have 2L here, you're squaring that term, right? So the doubling of L gets squared. It becomes 4 times, or a factor of 4 difference of P sub E. So it will, I may have said it backwards a second ago. P sub E will decrease by a factor of 4, okay? So one more time, if I were to say pi squared EI over K times 2L squared, what will this come out to? That'll be pi squared EI over 4KL squared. So P sub E will change by a factor of 4, and specifically P sub E will decrease by a factor of 4 because that factor of 4 is in the denominator, okay? So again, that's happening because of that squared term. So let's do another mental exercise. What happens if I triple L? What if I make, instead of L, what if it becomes 3 times as long? What will happen to P sub E? Well, you're going to have the 3, right? You have a 3 embedded in here that's then squared. That becomes 9, right? So 3 squared is 9, right? So that means that P sub E will decrease by a factor of 9, right? Because now you have a 9 in the denominator if L became 3 times longer. So these are fun little mental exercises to help you make sure you understand the implications of L, of the length of your column when you're calculating the Euler buckling force, because that L term is squared in there, okay? So again, great little quiz questions or test questions that some professors love to incorporate into some of their tests and exams, all right? So this is the background information of column buckling. If you found this helpful, please hit like and subscribe and be on the lookout for other things like this. Thanks for watching.